Welcome. Eaton Power Quality Division appreciates this opportunity to present to the Texas Energy Managers Association at the 2020 TEMA Conference. My name is ROrman. I'm the National Sales Manager for the Power Quality Division's Power Factor Correction, Surge Protection, and Power Conditioning units. I've been with the division for about 16 plus years. I've been featured speaker at a lot of technical seminars, conferences, CEU accredited seminars over the years, and recently a patent holder in surge protection technology. So we appreciate the opportunity, and let's jump right in. So, can customers save money on utility bills by installing power factor correction products? The quick answer is absolutely yes. If you are serviced by a utility that charges for poor power factor and your current power factor readings are low or poor. But don't take Eaton's word for it. You can look at the Department of Energy's website to find where they state low power factor is expensive and inefficient. Many utilities charge you for an additional fee if your power factor correction is less than a 0.95. Low power factor also reduces your electrical systems distribution capability or capacity by increasing current flow and causing voltage drops. But again, don't believe Eaton or take Eaton's word for it. You can see the full reducing power factor cost at the link below. So we know that power factor correction can save you money, but this brings up a lot of questions. What is power factor? How do I know if I have poor power factor? How do I know if I'm being charged a penalty by my provider? How do I know if installing power factor even makes sense for me? And then who can I get and help when pursuing a power factor project? So let's start off and kind of get back to the basics. What is power factor? Power factor is a measure of the efficient use of power, or the ratio of working power, kW, to apparent power, kVA. Those terms look pretty familiar, kW, kVA, but maybe the whole concept of power factor is a little confusing still, right? So let's take a more simplistic real-world look at it. If you own a factory, to do most functions in your facility, you need motors and other devices doing real quote-unquote work. In electrical terms, work is done by consuming watts, or kW, known as real power. Electrical equipment like motors require a magnetic field to be generated while producing the real power. The magnetic fields require reactive power to create that magnetic field. If you stop and think about it, if you walked up and pushed the start button on a full voltage non-reversing motor, what's the first thing that has to happen for the shaft to turn? You have to generate the magnetic field to turn the shaft. So this is that reactive power. Some people even refer to it as magnetizing power. It is measured in volt amperage reactive, or kVAR. And then finally, total power used by the system contains both kW and kVAR and is known as total apparent power. It is measured in volt amperage, or kVA. Total apparent power is typically delivered through a transformer. So that's why a lot of people recognize the kVA terminology, because typically the transformer out front of the plant is rated in kVA. When you go to school, you learn the power triangle, the relationship between kVA, kW, and kVAR. So here you can see on the horizontal axis, you have kilowatts, or your real power. You have your kVAR, or your magnetizing reactive power, on the vertical axis, and then the hypotenuse is your apparent power, or total kVA. So you can see the relationship there between the three. An even more simplistic way to think about it, and maybe even funny or comical, is to think of a beer mug. You know, if the beer mug is the transformer sitting out in front of your facility, you are currently pulling some ratio of beer and foam through your mug or through your transformer. So if you look at it, would you rather have a lot of foam or wasted capacity in terms of kVAR in comparison to watts? No, you would probably prefer to have more beer or more KW in that mug than there is foam. You would be using that mug much more efficiently. So the same thing applies to transformers. If you are using it and having a larger ratio of kilowatts versus kVAR, you're using that transformer in a much more efficient fashion. Certainly, utilities want to use their grid in the most efficient fashion. So they would rather minimize the amount of kVAR that they're pulling through their system and maximize the amount of kW so that they use their electrical grid as efficiently as possible. But uncorrected and left the way it is, what do you want to do here? You're looking at kW, kVAR being pulled through the system. The most efficient and better way to do it is to supply that reactive load uh, locally instead of pulling it through the electrical system. So you could supply the reactive power that the motors and things in your facility desire instead of pulling it through the electrical system. And it also makes it a more efficient, cooler running system as well. So those transformers will have that load removed from them, making them operate in a much more efficient, cooler fashion. So if you've ever looked at transformer curves, you know that for every degree that you can remove off a transformer, it extends the life of that transformer dramatically. So let's take a look at a sample and example. If we had a 125 kVA transformer and you wouldn't load it all the way up to 100%, but in this example, for simplicity, let's load this transformer all the way at 100% load, which would be putting a 125 horsepower motor on it. The motor wants to draw 150 amps and 75 kVAR. Again, it's drawing some ratio of kVAR and kW through that transformer uncorrected. So uncorrected, we see the power triangle on the right side of the screen. We have our 100 kW, the real work that it's doing. We see the 75 kVAR magnetizing power or reactive power that the motor wants to generate the magnetic field. And then we also see on the hypotenuse, again, what it's going to take in terms of total power to actually make this motor and this system work. If we look at it from a power factor perspective, you have 100 kilowatts divided by 125 kVA, that gives you a 0.8 power factor. Again, is there a more efficient, effective, and better way to do it? Yes, there is. You can come in and locally put a 50 kVAR capacitor there by the motor. This will now feed 50 kVAR to the motor, so I'm only pulling 25 kVAR through the system. So if we look now over to the right, we see that the work is still the same. The motor still is going to generate 100 kW of real work. But again, we're supplying 50 kVAR locally, so now we're only pulling 25 from the utility. And we see our hypotenuse, our total power drops from 125 to 103 kVA. So we're using our equipment more efficiently, not to mention that we would be able to add additional load onto this transformer because we now are operating at 103 kVA, freeing up some system capacity to add more load. If we look at our power factor, we see our original power factor was a 0.8, and now that we added this 50 kVAR capacitor, we now have corrected the power factor to a 0.97. A more efficient way to operate your system. So why would you consider power factor? Well, as we've shown, the number one reason is if your utility is penalizing you for poor power factor and you currently have poor power factor in your plant. But there are other benefits. As we just shown, you can reduce and you can use your system more efficiently. In the example we just shown, we lowered our system requirements from 125 kVA to 103. So we increased system capacity as we see here. So you'll increase capacity in your, all the way through your system. If you're correcting at the motor, you would increase the capacity of your MCCs, your switchgear, and your transformer feeding the plant. You're also going to reduce losses in transformers and cables. Anytime you flow ampacity, there's also system losses there. So if we are providing that reactive current locally to the motor, we're again not pulling it through our MCC, through our switchgear or our transformer. So we're going to reduce the losses in those types of equipment. We're also going to improve voltage regulation. If you're a plant where when the large motor starts, you see a momentary dip in your lights or in other equipment, you also will see some improvement in there as you kind of beef up the bus, because capacitors will resist voltage change, and it will help you with your voltage regulation slightly. Then finally, you're greening the power system. So a lot of companies are very, very keen to finding ways to be more efficient and improve and look at the environment. And certainly power factor correction capacitors use your systems more efficiently. So how do I know if I'm being penalized? Where do they appear on a bill? Well, identifying power factor can be, quite difficult. It can actually be spelled out and say power factor penalty. I haven't seen that a whole lot, but it can say power factor adjustment, power factor multiplier, reactive demand charge, or it can be a little more hidden by saying adjusted demand, which is actually the most common structure in the United States. So in adjusted demand, how would that work? Well, let's say a customer had an actual demand usage of 1,000 kW. The utility said, I want you to maintain a 90% power factor. The customer, though, was only maintaining power factor at 85% or 0.85. So they're 5% below where the utility wants them to be. So what happens on their bill? They take the 1,000 kW of actual demand and they adjust it by the 5% you're below their target, and they arrive at an adjusted demand of 1,050 kW, which is what the customer pays times their demand charge rate. So you can see clearly from here that they're paying 50 kW of demand that they do not have to pay if they would correct their power factor. What does this look like on a real bill? Well, here you can see it's very small, but you can see the base demand charge for this customer, is $8,500 or $6,500. And what they're looking at here is they have a 78.5% power factor. So they adjusted the power factor to 90%, and there's a $951.79 penalty that they're paying. So that adjusted demand down there could be eliminated. Here we see another example. This is kVA. So again, if your demand charge is based in kVA, what did we already determine? kVA has a kW component and a kVAR component. So if you can reduce the kVAR component, you can eliminate and reduce the penalty by lowering the kVA to where it more matches the kW. Because if you had no reactive power usage, your kVA would match your kW. So here you can see in this bill, their kW was 2,595. Their kVA is 2,969, and their power factor is a 0.874. So they could certainly reduce the demand charge that they're paying by increasing the power factor ratio more to unity, or closer to a 0.10, which would be eliminating the reactive power or drawing it down. And again, these can be very confusing. Here you can look at another bill. Are they paying a penalty? I'll give you the quick answer. They aren't, but it's very confusing with all the charges: renewable energy charge, transition charge, distribution charge. it's kind of tough to see a lot of times if you are paying a penalty. The good news is that Eaton's offers a free, confidential evaluation of utility bills. We can inform you of your utility rate structure, show you how you're being penalized, and you're more than welcome to take our information and our summary back to your utility to confirm that you are being penalized. So just a free service that Eaton offers. So if I'm being penalized, what are some of the offenders that are making me have poor power factor? Well, certainly one of the biggest offenders you'll find in any facility is going to be inductive motors. But there are also other sources. Anything that is an inductive load is going to contribute to poor power factor. So power transformers, welding machines, arc furnaces, inductors themselves, lighting ballast, etc., can cause you poor power factor. So I know what industry I'm in. What does the power factor look like typically uncorrected for my type of industry? Well, you can see all the industries here listed, and you can kind of get an idea of what your uh, typical plant uncorrected would look like. Excuse me. And again, another cost savings from power factor would be lowering, as we discussed, the operating temperature of your transformer. Well, how are we doing that? Well, if you remove that kVAR, that reactive power load from your transformer, you're not pulling it through your transformer. You're operating your transformer at a reduced temperature because you're freeing and removing that load from the transformer. So you can see here, this is a representation of that fact that you are removing load, operating it cooler, and which will extend the life of the transformer. Where would you put power factor correction? You can place it. The quick answer is you can place it where you need to. It can be right at the motor. It can be in the middle of your facility, and it can be upstream at the common point of coupling. There is no right answer to that question. The answer is to assess each location individually. If I walked into a plant and there was 2 or 3 large horsepower air compressor loads that contributed, to the poor power factor, I would probably try to place them at the motor. If I walked into a facility like a distribution facility and there was hundreds of motors all over, by the time you went around and installed smaller kVAR capacitors at the motor loads, you would probably, from an economic standpoint, be better off to come outside the plant at the common point of coupling and install the power factor correction there. I will say that the smaller type fixed capacitors at the motors, that business has kind of been declining for a number of years. And the larger power factor correction units placed at the common point of coupling, that business has been increasing over recent years. And there's a couple of reasons probably for that. One, if you know a lot about power factor correction, harmonics and power factor correction products don't play well together. So if you have air compressor loads, typically who has come in and tried to sell you what piece of equipment, there's probably been a variable frequency drive salesperson in there telling you how much money you can save by putting a VFD on that air compressor. So that means what? If you've put a VFD on an air compressor, that means there's harmonics floating around there. And so again, for simplicity and time's sake, we won't go into harmonics and capacitors, but you have to be a little cautious of what you're doing and know what you're doing when you're putting capacitors and VFDs very close to each other. On the other hand, the large kVAR units, the technology that was driving costs years ago was the controllers. As all electronics have done, controller costs have come down over the years. So that larger kVAR unit sitting outside your plant has gotten more economical, and putting the smaller ones close to motor loads has gotten a little bit more tricky. So that's probably the reason we're seeing the trend of increasing sales for large units and decreasing sales for smaller units. In our power quality labs, which we operate two in the United States, one in Houston and one in Pittsburgh area, we actually have real loads that we can hook up, capacitors, inductors, all kinds of our power quality equipment, and see what it does in the real world with real loads operating. So in our lab, we actually set up a example where we had a motor running and we're adding capacitors. So we could see what that looks like in terms of waveform and real numbers. So here you can see the waveforms. They're a little bit out of phase with each other. So we can see also below where the phase voltage is 69 volts. The current is 121. Total kW is 69. kVA is 96 and power factor is 0.72. So what do we expect if we add, you can see our increments there in the chart. We're going to add 15 kVAR. What do we expect to happen to the phase current and the kVA? We can see what happened. It dropped, which is what we would expect. Why did it drop? Because we're supplying a portion now of that reactive power from our capacitors. So we're supplying it locally and we're not pulling it from the utility. So as we add 15 kVAR increments, we can see this trend continuing, the phase current dropping, the kVA dropping, the power factor getting better. We started at a 0.72. We're at 8.7. We're at 9.4 now. We're at 9.8. We're at 9.9. So we're almost to unity. And now we can see our phase current has dropped from 121 down to 87. We can see our kVA has dropped from 96 to 70. Our power factor is obviously improved almost to unity. And our phase voltage has actually gotten a little bit better as well, which again is a side benefit. But what happens if we bring on another 15 kVAR? You can see now our waveforms up top are almost in phase. What's going to happen is we're going to cross over from a inductive circuit to a capacitive circuit. So we're all going to have the same problems now as we increase adding capacitors into this circuit, but we're going to cross over from an inductive circuit to a capacitive and kind of have the same problem. You can see that we now are consuming more kVA and more phase current in the capacitive circuit. So we are leading, what would be referred to as leading in capacitive leading. I'm going to back up real quick and scroll through these so you can kind of see, watch the waveform. So you can see we're out of phase, but the current waveform looks pretty clean. It does have a couple notches in it, but as we add capacitors into the circuit and come into phase with each other, you can see that the waveform is getting more distorted as we bring on more capacitors. And certainly as we cross over into capacitive, it's getting even more distorted from adding capacitors to it and amplifying some of the harmonics that may be present on this system. We also could show this from a phasor diagram standpoint. The numbers will be the same down in the lower right, but keep your eye on the phase. As you can see, we're adding capacitors. I start out of phase, come into phase there at 0.99, and then we cross over and start leading. So up to this point, we've been talking about power factor correction and what would be referred to as historic power factor or displacement power factor. That poor power factor coming from inductive loads in your facility like motors. But if you get a meter and you look at total power factor, that actually is accounting for two things. Historic or displacement power factor coming from inductive loads, but also a distortion element coming from nonlinear loads distorting the waveform. So if you look at the actual formula here, true power factor, you can see comes from displacement power factor times distortion power factor. What is distortion power factor? Again, it's coming from nonlinear loads, and it is distorting the waveform. And it also contributes. So you have two, you need to know what true power factor and your displacement power factor is, and you need to know both of those. Why do you need to know that? Well, if you just looked at your power factor correction here, your DPF, you can see that's your displacement power factor here. That is your inductive motor load power factor. So the DPF, the displacement power factor, is actually pretty good in this example. Let me highlight the bars here. But if somebody just looked at the true power factor, they would say, hey, we've got poor power factor. But what is the solution here? Can you determine anything from seeing these two values? Yes, you can determine something. That is that adding capacitors is not the solution here, because you don't have just poor displacement. You have poor power factor from actually distortion. So what this is telling you is that you have a harmonics problem in this building, and adding capacitors is not going to solve that solution. You need to be actually adding harmonic correction equipment in here to correct that poor power, overall power factor, because the displacement power factor is not bad at all. So there's different types of equipment. If I have harmonics, does that mean I can't use capacitors? If you have harmonics and poor displacement power factor, yes, you can actually add what is known as a filtered product to deal with the harmonic situation in your building, and or add, as we discussed, harmonic correction units to also address if you have tremendous amounts of harmonics in your facility. So what type of solution do I need? Do I need capacitors? Do I need standard or harmonically hardened because I have a harmonic environment? Do I need fixed or switched capacitors? If you go home at night and turn all of your equipment off, fixed capacitors will put you into a leading situation. So you may need switched capacitors. When you go home, it switches off with the load. As the load goes down, it takes banks of capacitors offline. If you have a harmonic environment, you may need a tuned or detuned or filtered bank. There's a lot of words for that. And we also, there's also manufacturers make low voltage, medium voltage. So again, it really determines the type of loads in your facility, whether a low voltage or medium voltage would be right for you, and what voltage you take delivery from your utility at. And then finally, if you have really bad and nasty harmonic environment, you may want a active harmonic filter to filter out the harmonics in your facility to give you a clean sinusoid. So I'm interested, what are the next steps? If you are a customer and you believe that you are paying a penalty and you want someone like Eaton or an engineering firm or anyone to outside your company to assess the situation, there's typically a letter of authorization that you can fill out so that the utility will release those bills to the company that you want to evaluate your situation and see if you're paying a penalty. Then once a penalty is established, yes, you are paying a penalty. Let's take a look at what your return on investment or payback would be. You can fill out the survey sheet to give us more exact information to take a look at what type of equipment would be correct for your solution and your application. Do companies, municipalities, and school districts install power factor and save money from it? Absolutely. In fact, Eaton has done projects with a number of industrial customers and educational facilities throughout the state of Texas. Educationally, recently we did some projects for Austin ISD and Texas A&M. So we have a lot of case studies, and we probably got one for your industry. So don't be hesitant to ask. There's a lot of them that are on the website. Here we saved a customer over $100,000 per year. So again, this can be a real cost advantage for a lot of companies. We also do have experience centers in our labs, our labs in Houston and Pittsburgh. So there is one in the state of Texas. We can demonstrate all these principles with real loads and real applications. So if you're ever in the area or want to learn more or come down and be educated, feel free. We also have on-site demo units that we can do on-site demonstrations. We also have calculators online where you can put your specific system numbers in and see if, what kind of kVAR you would be required and if there's any probability of resonating as well. Once you figure it out, we also have application guides that will help you figure out what family you would need, medium voltage, low voltage. You answer some questions and it drops you into one. There's also a educational Design It Right guide, which has been used by many educational facilities throughout the United States. This was originally developed by Commonwealth Sprague, which Eaton purchased Commonwealth Sprague years ago, but it will tell you everything and anything you ever wanted to know about power factor correction. So it has all the sizing charts, application guides, and more. So if you want to take a look at what do you do next, you can contact us and we would be more than happy to take a look at any of your applications, any of your facilities, and educate you more, even do CEU accredited classes if desired. So this line here, the TRC as we refer to it, Technical Resource Center, where there's 3 engineers that operate that line all day, every day during normal business hours and answer power quality questions of all sorts. So with that, I appreciate your time and allowing me to present. And if there's any questions, I think we'll be available for any answers.